Hi, my name's Paul Herman, and I've been a lecturer in School of Mechanical and Aerospace Engineering since 2005, but I also did my degree in the same school many years previous to that. So I have a good amount of experience of Queen's, both as a student as a member of staff. And hopefully, if you have any questions, I should be able to answer them for you. The building in which our school is based is the Ashby building. It was opened in 1965 and named after Sir Eric Ashby, who was a former Vice Chancellor at Queen's. He left here to go to be headmaster at the Clare College in Cambridge, and eventually became the Vice Chancellor of the University of Cambridge. And he had a very nice comment that he made in the opening address of the building in 1965. He wasn't an engineer himself, he was a botanist, but he had great respect for not just the architects who designed the building, but the technologists, the engineers that were going to be educated within it. And he hoped that they would use their knowledge of science and engineering and maths to improve things for mankind. And we think that that's a very nice ethos to try to uphold. Eric Ashby himself is a very well-respected person in the world of academia and spoke very well in support of technological disciplines and their importance in society in a broader sense. So the Ashby building is where our school is based, also part of the School of Electrical and Electronics and Computer Sciences is in the same building. We share it with them. But within our school, we have 3 undergraduate programs in aerospace, mechanical, and product design engineering. I'll describe a little bit about the differences and the similarities between those 3 undergraduate programs. We very much see that the discipline of engineering, and there are more than just the disciplines that we teach in our school, is all about taking that knowledge of science and applying it in a solution. It's something that works, something that does a job, and it's something that benefits society. And increasingly that means that our focus is changing towards things which are much more geared around sustainable development and how we actually maintain the planet while we increase our industry and the benefits to society. So the tall tower block, which is most visible, is about half of the floor space, and we have a lower 3-story building behind that, which is a large square block, which is all the laboratory, testing and project spaces. And we have some photographs here to show that those facilities actually underwent a major refurbishment. It started back in 2010 in different phases. So a lot of the equipment and the teaching spaces are very new and very much better suited to how our course delivery has changed over recent years. We do much more practical, hands-on design, build and test type experiences. And this has come, change in how we teach has come from our involvement in an initiative called CDIO. And that was started by MIT in Boston and 3 Swedish universities back around the end of the 20th century. We became the 5th member of that consortium in 2003, and it has grown to have over 100 universities across the world now involved in working together to try to enhance how engineering is taught so that our graduates are better prepared for professional practice. And key part of that is project-based and problem-based learning. But to be able to do that, you need to have the appropriate workspaces and facilities for students to be able to learn in that way. So right from first year in our introductory courses, which set the context of what the discipline is like in professional practice, students are working in teams, developing not just technical knowledge and how to apply that, but also learning how to work together and how to conduct the discipline in the way that it will happen after they graduate. It's not a case of just being able to learn the stuff and pass exams. Engineering is much more than that, and management and team working skills and communication skills are a very important part of that. So we have things right from first year that help you develop these what are sometimes called professional skills or softer skills, as well as your technical knowledge and the application of that. And then through into second year, all of our students on 3 different undergraduate pathways will take part over the course of the year in making their own little oscillating engine that runs on compressed air. So you make every part, cast some parts, machine some parts, weld the frame up, do some of the ridering, CNC machining, and then assemble it all and then test it on a test rig that was the lecturer who runs the course actually designed in our workshop made for testing the kit. And the graph in the top right, you can see there is the performance of one of the engines, and all of the other grayer lines are the performance of other students in the class. So this helps you understand that, you know, if things don't fit together very well, if they don't run smoothly, it actually impacts on the performance. And you can see the stage 3 mechanical engineers are involved in designing and building their own folding bicycles for urban commuters. This starts off in the top left with making sort of little paper scaled versions, cardboard and paper, and then moving on to model it on CAD. We have a prototyping facility, the Student Design Centre, where they have laser cutters and 3D printers, foam cutters and so on. They make a full size mock-up to test how it's going to fold and fit. And in that year, the challenge was to fit, you see bottom centre, fit the folded bicycle inside one of the lockers. This year, we've changed the brief. They have to fit it inside a suitcase. So the real experience here is that you design the parts that get made in the workshop, the students assemble, they also source other components such as gears and pedals and wheels and so on, assemble it all together, and then we go racing against each other. So we have slalom courses and laps of the buildings and stuff. Always has worked out so far to be a good day around May time when we do this. We're very fortunate. But it's only by sort of riding your own bicycle that you have designed and had made that you understand how good your design was. So it's actually direct feedback and a very practical application of your skills and chance to also be better than the other teams in your group. So there's a competitive element which the students thoroughly enjoy. The 3 different disciplines then within the school, the biggest is mechanical engineering. We have typically about 100 to 120 students in that cohort each year. It is very much more than what might be the first perception, which is that it's all about machines and engines. Yes, we do cover that, but there are many more other things that might come as a surprise, such as prostheses and hip joints and tissue scaffolds. We also have a centre which looks at processing of polymers, the optimization of the manufacturing of polymers, the use of alternative materials and composites, and so on. We have work going on with nano tubes and nanoparticles within composites to try to enhance properties and bring new products to market. We also have people who are working on renewable energies and other types of alternative forms of energy and clean energies, which is a major focus and shift from where we were maybe 20, 30 years ago. On the mechanical engineering undergraduate program then, you'll see a number of common themes through our pathways here, is the first and second year are core mathematics and engineering science disciplines, so thermodynamics and fluids, statics and dynamic forces, materials and material properties. And then within mechanical engineering, there's a focus on engineering design, manufacturing. Computer-aided analysis is this type of picture which you're seeing over in the center right, which is a finite element analysis. That's how you can make a computer model and apply material types, different constraints and different loads onto the part and change your design and iterate it to be optimized before you ever make a prototype or make a real thing. And that's part of the validated simulation. We then go on and make physical prototypes and test that the calculations on computer in a 3D modeling sense were correct. Also, and this sometimes surprises people, is that there's an aspect to engineering which is more geared towards management and we're preparing people to be leaders and managers in industry, not just assembly workers and so on. So the engineering degrees is all about becoming a professional and getting professional accreditation. So you cover things like company law, employment law, management skills, micro and macroeconomics, and how to keep and do accounting and things like that, which are all very important skills for managers in industry. Aerospace engineering then differs significantly after first year from mechanical engineering, and there's more of an emphasis on designing things that will fly or move through fluids effectively. So they may be planes, helicopters, drones, but also satellite and things that go into orbit. And we have one lecturer in particular who does a lot of work with other Irish universities in putting cube satellite units for analysis up into space. Aerospace engineering then is not just about planes. I mean, a lot of the skills transfer into other industry sectors, such as the automotive industry. And because making planes is very much at the forefront of manufacturing lightweight structures, those types of skill sets are very transferable to other industries as well. So like mechanical, you have your core maths and engineering science, but then there are things which are specific to the design of aircraft or vehicles, such as flight mechanics, propulsion, and for the aircraft design. You actually need very few parameters defined to be able to go and design an aircraft. It's things like how far do you want to fly and how much mass do you want to have to be able to carry or transport. And you want to do it with using as little fuel as possible. So from that, from those few parameters, it leads to very, very complex, many thousands of components, systems engineering type approach that things have to work together and have to have complex control systems and so on. And again, the same professional studies track applies equally well to people on the aerospace program. Our product design engineering program then is slightly different, although it is quite closely related to mechanical engineering, but it has more of a focus on the design process and a little bit more on the ideation, how to come up with the idea and identify where there's a customer need or problem, and also through to the commercialization, the bringing it to market and the business aspect. It's a slightly broader, fewer or less depth in some of the specialisms like thermodynamics and so on that will be on the mechanical program. The product design program was indeed the area where we first introduced the design, build, test approach from the CDIO initiative, but that is now spread out through all of our undergraduate programs equally. But it was very much the new program that was introduced in 2004, in which all of this new side of teaching was developed. So there is an emphasis on design and manufacturing and materials, perhaps more so than the mechanical program, but there is a lot of similarity. Okay, some information about the school then. We're about roughly the size of a local secondary school in terms of about 1,000 students in total. We have 45 teaching staff, but we have many other research staff and technical staff and clerical and administrative support people. So we have over 100 staff in total. The bulk of our students currently are in undergraduate pathways, so we have about 750 with just under 70 students studying for master's level qualifications and just about 100 studying for PhDs with us. We have 20% of our students are female, which is much higher than the UK average for engineering or technical disciplines. And 18% of our students are from outside of the European Union. Our high percentage of female students is no coincidence. We are a proud holder of a Silver Athena Swan Award, which is all about having an environment which is fair and equitable to everyone and no one is disadvantaged. So we welcome students from all countries and of all genders into our school equally. And that's potentially a perception that engineering is very much a male-dominated discipline. Yes, we do have more male students, but the female students actually attain very well, and we have a slightly disproportionately high number of award winners at our prize giving each year are female. This will probably be a little small on your screen. I'll try to describe what it is. You won't necessarily be able to read all of the words, but the three columns show the aerospace on the left with some blue tiles, mechanical up the middle with green, and product design with red. Now the tiles, or the cells that are coloured in, refer to modules. If it's not coloured in, it means that it's taught on more than one pathway. So in first year, pretty much everything is the same, except that the introductory courses, those are the small group project type activities in first year. They're slightly different if you're doing aerospace, mechanical, or product design, and the themes of your projects will be geared towards those disciplines. But everything else in first year is the same. And this allows the possibility, once you're in the school, to transfer between any of the three pathways after first year. Perhaps you think that mechanical engineering was your thing, but while you're in the school, you think that perhaps aerospace or product design is actually better suited. Having maybe spent some time seeing what other senior students are doing, being aware of the projects or the research that's going on in the different disciplines, you might think that that's a better switch for you. You might be aware of where students are going in placement from the senior years and so on, and change your mind. So that's possible at the end of first year, assuming that you're passing all of the modules. Then, particularly if you notice in second year, aerospace is quite different, and there are a number of modules which only appear in the aerospace pathway. Mechanical and product design, still very, very similar, with a lot of the modules being taught across, and some of these ones at the bottom being taught across all three pathways. And then once you get into third year, it's the final year for bachelor's students, then there are more significant differences, and the big box there is the individual project. For graduating students, or the group project, that would be things like model aircraft design and build for aerospace students, and folding bicycles for mechanical students, and designs of their own for the product design students. So that's where the difference comes in the projects in third year. Okay. For students who are staying on to do MEng, and it is possible even if you start as a BEng student after second year, if you're doing well, you can transfer onto the MEng pathway. Then there are more specialist discipline-specific modules in fourth year. And each student always does an individual project, which is a third of their final year. So there's a large chunk at the top there, which is individual projects. Another thing which we feature significantly in our pathways are years in industry. Over the last 10 years, so we've grown the number of students taking a year out from about 20% to, at a peak in 2018 graduates, it was 2/3 of the students had 67% had done a year in industry. It's a little bit lower last year. But the general trend has been very much upwards. We have many companies coming back looking for another one of our students each year, because they've been so impressed by the students that go out. And the students are given very responsible roles within the companies. It surprises me sometimes when I read their portfolios, how much responsibility and what good experience they're getting, and how much they learn and add to their technical knowledge from doing the year out. We insist that all of the placements are paid, and we need to see a contract of employment and a job description. We need to see all the insurance and liability covers in place for the student, and we do send our placement officer out to visit each student or an academic while they're on placement. We have 3 years in a row, 2017 through to 2019, where we won the national undergraduate employability awards for the best contribution to small or medium-sized companies. So that's a UK-wide award, and students from our school won that award in 3 years in a row. So we're very confident that not only are our students good, but the placements that they're getting are good and recognised as being such at the UK-wide level. We also have what's known as our engineering leadership program. This is where we partner students up at the end of first year with a number of companies. The company will then offer them their year out sandwich year, but also the companies provide seminars throughout the year as extracurricular activities for the students that are on the pathway. So it is a competitive process to become part of the engineering leadership program, and there's an assessment centre which we run at the end of first year in order to identify students. It's not necessarily the students who are the highest achieving academics, it's the ones who perform well in the assessment centre, which looks at things like team working and communication. So we're looking for people who are well-rounded that will be future leaders in the companies. And we have a number of local and UK-wide things. My screen is showing my picture hiding the likes of Aston Martin. So Aston Martin, GlaxoSmithKline are UK-based companies that also are involved in our program. We've had tremendous success in the Royal Academy of Engineering Leadership Scholarships. These are worth about £5,000 to students, and there are about 35 handed out across the UK each year. And we have been very successful in recent years with some of our students winning these awards. So I think in 2016 was the best, when we had, I think it was 8 winners out of 35 in the UK. So again, the leadership and the management skills that we're building into our program is being recognised at a UK-wide level. They're producing excellent graduates who are very employable. We're very fortunate to have a number of people who've set up trust funds and things which benefit our students, scholarships and awards. We have some companies, we have some individual families who've done well having been graduates who then want to put something back in. So last year we handed out over £160,000 in scholarships and awards. The smallest of those is around £200, but we have ones which are worth £10,000 per year to students, which more than offsets in a lot of cases offsets the tuition fees. Some of the awards and scholarships are geared towards female-only applicants to try to encourage more females into the discipline. Some are geared towards students who come from low-income households to try to make it easier for them to be able to come to university. But it's a significant number, and it's a bigger scholarship fund than most schools in the university. At the end of the day, we're all about producing graduates who are going to go into employment, and we're very proud of our employability record of graduates from the school. First thing which is important is all of our undergraduate degrees are accredited. The AEROSPACE degree by the Royal Aeronautical Society, and Mechanical and Product Design Engineering by the Institution of Mechanical Engineers. They come to visit us every 5 years. We had our most recent visit in April 2019, and any graduates right up to the next 5 years are fully accredited. And that's the first step towards becoming a chartered engineer. Throughout our 3 or 4 years of your degree program, there are a number of activities geared towards preparing you for employment. So we do first professional development planning in first year with students, trying to encourage them to add to their skills, not just get their degree, but do other things which are complementary throughout their time at the university. And there are many fantastic opportunities for co-curricular, extracurricular activities, numbers of clubs and societies within the university. So we want to encourage people to come and do more than just study, try to build and broaden their skill set in other ways. In second year, we have the employability program. That's where our employability officer helps prepare people for identifying, applying for and winning their year out placements. Third year, then we have a number of recruitment fairs and assessment centre type activities, seminars and stuff that run on a drop-in basis in different days throughout the year. And then the engineering leadership program runs for students who are on that for second and third year. We also have a growing number of industry-backed final year projects, and this year we had 25 people doing their final year project in association with the company. And that, again, that's an excellent way to build up very valuable skills for your CV. And in a number of cases, that leads to the company being so impressed by the student who did the project that they end up working with them once they graduate. Okay, so some employability facts. We like to focus on students who get a job in the discipline. So 86% of our graduates are in graduate employment that needs their degree after 6 months, and that's higher than the UK average. We have even higher percentage are in graduate employment for the discipline if they've completed the sandwich year, the year out placement. So that is a definite boost to your employability. The average starting salary last year for graduates from the school was just over £24,000, which again is higher than UK average for graduates from all disciplines.